So why would the third object from interstellar space be aligned so well with the planets unless its trajectory was designed by some intelligence for a reconnaissance mission?
NASA has been watching. For nearly 40 days, their spacecraft locked onto a single comet, imaging it every 4 minutes without stopping. This has never been done before, and what they captured in those thousands of frames is forcing scientists to rethink how we monitor threats from deep space. Between August 25th and October 2nd, 2025, NASA's Punch mission executed the longest high-frequency tracking operation of any comet in recorded history. The target, Comet C/2025 R2, also known as Comet SWAN. Every 4 minutes for 39 days straight, NASA's instruments captured this icy wanderer as it drifted through the inner solar system. The result is hundreds of images stitched into a continuous surveillance record that reveals not just where the comet went, but how the sun's invisible forces are shaping the space around us in real time. This isn't just about one comet. This is about NASA testing a new capability to monitor solar wind, space weather, and potentially hazardous objects with unprecedented precision. And the implications reach far beyond astronomy. Here's what we know. Comet C/2025 R2, SWAN, was first spotted in September 2025 by Ukrainian amateur astronomer Vladimir Bezugli. He wasn't using a telescope. He was scanning publicly available images from the Solar and Heliospheric Observatory, SOHO, a sun-watching satellite. Bezugli noticed a bright blob near the sun that shouldn't have been there. Within 24 hours of its discovery, the comet reached perihelion, the closest point to the sun in its orbit. It passed at a distance of 46.74 million miles, 75.20 million kilometers from our star. The moment sunlight hit the comet, it began to change. Early images revealed a bluish-green coma, a glowing cloud of gas surrounding the nucleus. This happens when the sun's heat vaporizes the comet's ices in a process called sublimation. Gas and dust are released, then swept backward by the solar wind, forming the glowing tail that makes comets so visually striking. But by mid-September, something unusual happened. The coma took on a triangular shape. Astronomers call this a hammerhead distortion. It's not normal. It's a sign that the nucleus may be fragmenting. When a comet breaks apart, outgassing from multiple pieces stretches the normally round coma into a lopsided triangular form. NASA was watching this happen in real time. And they weren't just watching Comet SWAN. At the exact same time, another object was sharing the same patch of sky. 3I ATLAS, an interstellar comet from beyond our solar system. In the punch time lapse footage, 3I Atlas appears briefly near the end of the sequence, zipping from left to right beneath SWAN. Two comets, one from our solar system, one from interstellar space, both under NASA's lens at the same moment. The images show Comet SWAN moving leftward across the frame. But here's the critical detail. The tail is also being pushed in the same direction by the solar wind. This makes the comet appear to drift backward, as if retreating from the sun while still moving forward. That backward drift is not an optical illusion. It's the solar wind, a continuous stream of charged particles flowing outward from the sun, physically pushing the comet's gas and dust in the opposite direction of its motion. By late October, Comet SWAN made its closest approach to Earth, 25.10 million miles, 40.38 million kilometers. That's close enough to be on the cusp of naked eye visibility. Anyone with binoculars or a small telescope could have seen it. Most people didn't know it was there. Now let's talk about what this really means. NASA's Punch mission isn't just taking pretty pictures of comets. It's studying the solar wind, the invisible force field generated by the sun that shapes the entire solar system. Comet tails act as natural tracers of this wind. By watching how the tail moves, bends, and reacts, scientists can map the solar wind's speed, density, and turbulence in ways that satellites alone cannot measure. This matters because the solar wind doesn't just affect comets, it affects everything. Satellites, astronauts, power grids, GPS systems, communications networks. When the sun releases a powerful burst of energy, what we call space weather, it travels along the solar wind and slams into Earth's magnetic field. If the burst is strong enough, it can knock out electrical systems, scramble radio signals, and disrupt global infrastructure. NASA is now proving they can track these invisible forces continuously in real time with unprecedented resolution. The 4-minute imaging cadence means they're not just checking in than once a day. They're watching every shift, every ripple, every change as it happens. This is surveillance level monitoring of space itself. And it's not just about defense, it's about prediction. If NASA can track how solar wind interacts with comets this precisely, they can start predicting how solar storms will interact with Earth. That means early warnings. That means time to prepare. That means the difference between a regional blackout and a global catastrophe. According to Craig DeForest, the principal investigator for the Punch mission at the Southwest Research Institute in Colorado, other comets have been tracked at once-per-day intervals for years, but the few-minute cadence of observation is what makes this unprecedented. He stated clearly, "What's new here is the few-minute cadence of observation." That statement is critical. Once-per-day tracking gives you snapshots. 4-minute tracking gives you a live feed. The difference is not incremental, it's exponential. NASA heliophysicist Gina DiBraccio, acting director of the Solar System Exploration Division at NASA's Goddard Space Flight Center, emphasized the broader mission. Watching the sun's effects from multiple vantage points and with different types of instruments is what gives us a complete picture of the space environment. We use these same tools to track and analyze how space weather impacts our astronauts, our spacecraft, and our technology here on Earth. Investigators and analysts within the space weather community are now treating this mission as a proof of concept. If Punch can do this with one comet, it can do this with solar ejections, with plasma clouds, with radiation bursts. The technology is no longer theoretical, it's operational. Oh, here's where it gets more serious. The fact that Comet SWAN's nucleus may have been fragmenting is not just an astronomical curiosity. Fragmentation increases the surface area exposed to the sun, which accelerates outgassing. That means more material being ejected into space. More material means a larger interaction zone with the solar wind. A larger interaction zone means more data, but it also means more unpredictability. If a comet fragments near Earth's orbit, the debris field can spread. Some fragments may vaporize, others may persist. The solar wind pushes them, but gravity and orbital mechanics pull them in different directions. Tracking a fragmenting comet at 4-minute intervals allows NASA to see exactly how that debris disperses in real time. This is the same capability needed to track potentially hazardous asteroids, space debris, and unidentified objects entering the inner solar system. And let's not ignore the elephant in the frame. 3I-ATLAS, an interstellar comet, a visitor from another star system. NASA captured it on the same footage, moving through the same region of space as Comet SWAN. That's not a coincidence. That's a convergence. Two distinct objects, two different origins, both interacting with the same solar wind at the same time. NASA now has comparative data on how interstellar material behaves versus solar system material under identical conditions. This is not just science. This is reconnaissance. The Punch mission has just demonstrated a level of space monitoring that most people didn't know was possible. Continuous, high-resolution tracking of moving objects across the inner solar system. Real-time observation of solar wind interactions. Detection of fragmentation, outgassing, and structural changes in comets as they happen. But here's the critical question. If NASA can do this with a comet, what else are they tracking? Space is no longer a place we visit occasionally with probes and telescopes. It's becoming a monitored environment. The ability to image an object every 4 minutes for 40 days means the ability to maintain persistent surveillance over vast regions of space. That capability extends far beyond comets. It applies to satellites, debris, near-Earth objects, and anything else moving through the solar system. The fact that Comet SWAN was visible to the naked eye, or nearly so, by late October, means it passed within 25 million miles of Earth. That's close, not dangerously close, but close enough to matter. And NASA was watching it the entire time, frame by frame, minute by minute, from the moment it entered their field of view until it drifted beyond range. This mission proves we now have the tools to see threats coming. The question is whether we have the infrastructure to respond. Solar storms, comet fragments, rogue asteroids, they don't wait for us to be ready. They happen on their own schedule. The difference between disaster and survival is how much warning we get. NASA just showed us they can give us that warning, but only if we keep watching. This is just the beginning. NASA's Punch mission is still operational. More comets will enter the inner solar system. More solar storms will erupt. More objects will pass close to Earth. And now, for the first time, we'll be watching all of it it in near real time. Subscribe for more updates as the truth continues to unfold.